So today we're going to be looking at the first new topic on the course, which is the idea of programming with effects. And we're going to start off by asking a question, and it's a question you can ask about your life, but also about your programming languages. And the question is, shall we be pure or impure? So what do the words pure and impure actually mean in the context of programming languages? Well, a language is called pure if the programs are mathematical functions. And what this means is that the programs simply take all their input at the start and give all their output at the end and don't do anything in between. They don't have any interaction with the outside world via some kind of side effects. They're just pure mathematical functions. And Haskell, which we're studying in this course, is the classic example of a pure programming language. We also have impure languages, and impure languages can have side effects. So in an impure language, the programs can have side effects. And side effects are things like input-output, like state, and exceptions. And classic examples of imperative or impure programming languages are things like C and Java. So both of these kind of programming languages have benefits. Pure languages can benefit from simple mathematical reasoning, and that's something we're going to see in the second half of this course. And pure languages can also benefit from lazy evaluation, which is a powerful new way of thinking about structuring your programs. On the other hand, impure languages may be faster, although these days I'm not sure that's actually such a true statement anymore. Something like the Glasgow Haskell compiler can produce highly optimized code, which is comparable with optimized code for other languages. But the fact of the matter is, we actually do need effects, and that's one of the main benefits of impure programming languages. If we want to write real programs, we have to interact with the outside world via some kind of side effects. So this raises a question: can we combine the benefits of the two approaches? Oops. Can't spell. Let's get rid of that. It's two approaches. Can we combine the benefits of the two approaches? And the answer is yes. And the answer to this question in this course is the idea of monads. So if you took the first year functional programming course with me in Nottingham, you've actually seen a little bit of monadic programming when we saw how to write programs that deal with input-output. But I didn't actually bring out the full concept of what a monad is. So that's what we're going to be doing here. And for me, monads are one of the most important new ideas in computer science in the last 25 or 30 years or so. So what we're going to be looking at in the first half of the Advanced Functional Programming course is an introduction to the use of monads for programming with effects in Haskell. And what I'm going to be doing is working pretty systematically through chapter 12 of my Haskell book, the chapter on monads and more. So you probably want to have a look at that if you're trying to do well on this course as well. So what we're going to start off with is the idea of abstracting programming patterns. And monads, as we'll see, are an example of this idea. So I'm going to come at this by means of a couple of examples. So let's first of all imagine that we were wanting to write a function which increments all the elements in a list of integers. So we could define a function called inc, and it takes a list of integers and it gives you back a list of integers. And we won't try and be clever here, we'll just define it using brute force recursion. We'll say if you increment an empty list, you get the empty list. And if you increment a non-empty list, where n is the first thing, n's is everything else, all you're going to do is add 1 to the first thing, and then you're going to increment everything else. So a simple two-line recursive definition. Let's imagine then we want to implement another function called square. And what square is going to do is take a list of integers and it's going to square each number in the list. So square is going to take an empty list and give you back an empty list, and square of a non-empty list is going to be, we square the first thing and then we square everything else. So again, a simple two-line recursive definition. But you see, we're using exactly the same programming pattern in both cases. In the base case, in increment, we're taking the empty list to the empty list, and it's the same with squaring. Empty list goes to the empty list. And in the non-empty list case, what we're doing is recursively processing the first thing. Sorry, that's not correct. We're simply processing the first thing, and then we're recursively processing the tail of the list. And the only difference is, in the increment case, we're applying the increment function here, and in the squaring case, we're applying the squaring function here. But apart from that, these two functions are basically the same. They use the same pattern of recursion. The base case maps the empty list to the empty list, and the non-empty list case maps to processing the first element and then recursively process everything else. So what we've seen here is we've got a common pattern which we can abstract out. It's the idea of kind of doing something to every element of a list. And of course, when we abstract this programming pattern out, we get our old friend, the map function. So let's define map. So map is a higher order function. And what it does is it takes a function from A to B, and it takes a list of A things, and it's going to give you back a list of B things. And the way it works is it's defined using simple recursion. If you map a function f across an empty list, there's nothing to do. And if you map a function f across a non-empty list, what you're going to do is apply the function to the first element, and then you're going to recursively map the function across the remainder of the list. And this higher order function, called map, because it's taking a function as its first argument, that's why it's higher order, captures the pattern of processing each element of a list by simply applying a function to each element in turn. So we've observed the common pattern and we have abstracted it out. And the benefit of this is that now we can define functions such as increment and squaring in a much shorter way. So let me define increment. I could say increment of n's is map of +1 of n's. Or if I wanted to be clever, what I could do is cancel the n's on both sides and simply say that the increment function is the function that maps +1 across a list. And similarly, I could define the squaring function to say it's just mapping of squaring. Okay, so what we have done then, just to summarize, is we've given two simple examples of simple recursive functions on lists. We've observed that they've got a common pattern. It's just applying a function to each element in a list. We've abstracted that out and we've obtained the map function. And then using the map function, we can then benefit from that, and we can define other functions such as incrementing and squaring just by instantiating this general pattern. And as I said a few moments ago, the reason we're thinking about this is monads are an example of abstracting out a common pattern. So let's now generalize a bit further from the map example. So we're going to think about generalizing further. So the idea of mapping a function over each element of a data structure turns out not to be specific to lists. You can map over lots of different data structures like trees and so on. And this leads us to the idea of what's called a functor. And a functor is one of the stepping stones to understanding and defining what a monad is. So I'll go right in and give you the class definition for what a functor is, and then we'll explain that, and then we'll see some examples. So here's the class definition for a functor. So something called f is going to be a functor provided it's got a suitable mapping operation. And the keyword or the identifier map is already used for the map function on lists, so we call this fmap, just so we don't have a name clash. And fmap has exactly the same type as map, so it takes a function from A to B, but rather than taking a list of A's, it takes an f of A to an f of B. So this is the definition in Haskell for what it means to be a functor. So let's understand the component parts of the definition. So let's look at the header first of all. So what it's saying is a parameterized type, f, is a member of the functor class if it has this particular function fmap. And we know that f must be a parameterized type because we can see it here being applied to a parameter. We've got f of a and f of b. And a parameterized type is simply something like list or tree or so on, which takes a parameter. So you have a list of a's and you have a list of b's, or you have a tree of a and a tree of b's. Okay, so when Haskell sees this declaration, it knows that f must be a parameterized type, and it's a member of the functor class provided that you can define an fmap which has this type. So what fmap is doing is it's generalizing the idea of mapping to any parameterized type f. And you might be wondering, well, where does this funny word functor come from? Well, the term functor comes from a branch of mathematics called category theory, which is concerned with the study of algebraic structure. And actually, the more you know about functional programming, the more you realize that category theory has had a heavy influence on languages such as Haskell. Okay, so what we've done now is we've generalized the idea of mapping to any parameterized type f, which supports a suitable fmap of this type. So let's have a couple of examples of this now. So the first example we're going to look at is the list functor. So how do we define the list functor? So we make an instance declaration and we say instance functor list, and I'll come back to what this means in a minute, where, and then we can simply say, well, let's actually write the type down first. We can say fmap goes from A to B to list of A to list of B, and we can simply say that fmap equals map. Okay, so there's a few bits and pieces to explain in here. First of all, what is this? This looks like the empty list here, but actually it's not the empty list. This is the parameterized type of lists where we haven't given it an argument. So actually what's going on in Haskell, when you write something like the type list of A, what that really means is it's the type, parameterized type list applied to A. So the empty list here is really being overloaded. So in this context, it's like when you write tree of, you write tree, and when you write list of, you can write this this empty list here, and that means the parameterized type of lists. So what else have we got? Oops, let's get rid of that again. Then we have a type in here. And what the type is saying is we've just instantiated the type of fmap. So fmap goes from A to B to f of A to f of B, but what we have here is the instantiated version of that. So fmap in this case goes from A to B to list of A to list of B. Okay. You might be wondering, why did I write a comment symbol here? Well, for some funny reason, Haskell doesn't allow you to make type declarations in instance declarations, but it's very useful to do so because these are useful for guiding the definition. So later on, when we define more complicated functions as instances of classes, having the type of the thing we're trying to define actually turns out to be very useful to us. So I'm always going to write down the type of things, but I need to write it in a comment. And then last of all, we don't need to give an explicit definition for fmap because map is already defined in Haskell, so we can just write fmap equals map. So that's the list functor, which we're already very familiar with. So let's have another example of a functor. This time we're going to look at the maybe functor. So what does this do? So let me first of all remind you about the data type maybe A. So this is a very standard built-in data type in Haskell. So the way it's defined is maybe A. It's a parameterized type, so we can think about making it into a functor. And it's got two values or two constructors. It's got nothing or just of A. So this is the built-in type maybe of A, and again it's a parameterized type because we have a parameter sitting here, and we've got two constructors, nothing, which we typically think of as representing something which has failed, and just of A, which we think of as representing something which has succeeded. So for example, if you had a value of type maybe int, it could either be nothing or just of a particular integer. So it's a parameterized type. So now we can think about making it into an instance of the functor class. So we can write instance functor maybe, where, and then I'm going to follow the same pattern as before. I'm going to write down the type of the fmap, and again I have to write it as a comment because Haskell doesn't allow us to make type declarations in instances. So fmap is going to take an a to a b, and this time the function which we're working with, or the parameterized type rather that we're working with, is maybe. So we go from maybe of a into maybe of b. So that's the name of the game. So how do we define this? Well, let me first of all write down a skeleton for this, which is a good way to proceed. So we can say fmap, let me call the parameter here g, so I don't get confused with the use of f for functors. So when we're mapping a function called g, there's two cases. We could either have nothing, and we'll figure out what to do, or we could have just of x, and then we can figure out what to do as well. So this is where types are going to help us. So what we need to do is we need to return in each case something of type maybe b. So we need to figure out how can we build something of type maybe b based upon what we have. Well, in the base case, there's not an awful lot we can do because we don't have anything. We just have nothing here. So what can we write on the right hand side? And if you think a bit and you scratch your head for a bit, you'll realize the only thing that we can write on the right hand side here is actually nothing as well. And that's because nothing has type maybe a for any a, so it could have type maybe b. So that's fine. Then we think about the second case. How do we map a function across a just? Well, we can think about the types involved here. If we think about what is the type of x, well, the whole type of this is maybe a, so that tells us that the type of x is a. So how can we get a maybe b out of this? Well, if we think about the type of the function g, let's write it down. So g has type a to b, x has type a. So we've got a function, we've got an argument. The obvious thing to do is just apply one to the other. So we could apply g to x, and that has type b. But we don't want a b here. What we actually want is we want a maybe b. And there's a simple way to convert a value of type b into maybe b. It's simply to write just in front of it. So if I write just of g of x, then that will have the right type now. Okay, so this is the mapping operation on values of type maybe of a. And it does exactly what you would expect. In the nothing case, it just maps nothing to nothing. And in the just case, it simply applies the function to the parameter value x and then retags it as a just. So it's like a degenerate example of the list functor, where we either have nothing in the list, which is nothing, or you have one thing in the list, which is like just. So let's have a couple of examples of this to make sure everyone understands what's going on. So if I started up GHCI, the maybe instance of the functor class is built in, so I can try that out. So I could say, what is fmap of +1 to nothing? And of course, I'm just going to get back nothing. So what you see here is the fmap is propagating the failure. We're applying fmap to nothing, and what we get back is nothing. So it's kind of propagating failure for us. And then if we consider the success case, if we apply fmap of ×2 to just of 3, then it's going to do the mapping operation. It's going to apply the function ×2 to 3, and we'll get 6, and then it will retag it as a just. So we'll get just of 6. So what's happening in this case is in the case of success, where we have a just value, we're applying the function, in this case ×2, inside to give the result just 6. So one more example here, just to kind of emphasize the point. If I did fmap of the negation function not, and I applied that to just of false, then it would give me back just of true. So again, it's just the simple mapping operation for the maybe type. So we've had two examples now. Let's have one more example. Let's look at binary trees. So what we're going to look at now is the idea of the tree functor. So let me define a simple data type of binary trees. So I'm going to define or declare a new data type called tree of A, and it's going to have two constructors. It's going to have a leaf constructor, which takes a value of type A, or it's going to have a node constructor, which takes two subtrees. Okay, so what we've declared here is three things. We've declared a new parameterized type called tree, and it has a constructor called leaf, which takes a single value of type A as a parameter, and it's got a constructor called node, which takes two recursive subtrees as parameters. So what we see then is that this tree data type is the data type of trees with data in the leaves. So a simple example of this is I could have, if I said T is a tree of integers, I could have a little example that says I've got a node, and then I've got a leaf with 1 and a leaf with 2. So this would be an example of a tree in this data type. So tree is a parameterized type, and whenever you see a parameterized type now in Haskell, you should think, can I make it into an instance of the functor class? So let's see how we can do that for the tree data type. So we'll follow the same pattern, which we've seen now a couple of times. We're making an instance declaration, and we're saying that the tree data type is going to be a functor. And we follow the same pattern again. We write down the type of the fmap. So fmap is going to take a function from A to B, and this time it's going to take a tree of A, and it's going to give me back a tree of B. And again, I need to put this in a comment, but the type is very useful for guiding the definition of the actual fmap function. So let's begin again by writing down the simple skeleton. So we say fmap of G to a leaf X is going to be something, and then fmap G to a node with a left subtree and a right subtree is going to be something. So let's think about the types of everything involved here. So we've got a function called G, and G takes an A to B, and we know that just by simply looking at the type. fmap, the first parameter, is going to be a function from A to B. So we know what the type of G is. We also know what the type of X is because the second parameter is a tree of A's. So we know here if we have a leaf, then the value X is going to have type A. So we can write that down as well. So we can say X has type A. And then finally, we know because we have a tree of A coming in as the second parameter, we know that the two parameters to node must have the same type again. So we know L is a tree of A, and we know that R is a tree of A. So we have L and R both have type tree of A. So that's the components we've got to play with to try and complete the right-hand side of the definition. And again, we're trying to build something of type tree of B. So how do we do this? Well, in the base case, what have we got? Let's have a look. We've got a function G from A to B. We've got a value X of type A. So again, just like we did in the previous case, we could apply one to the other, and that will give us a value of type B. And then, just as in the previous case, we'll retag that, and that will give us a tree of type B. Because if I just had G of X, that's just a B value, but I need a tree of B, so I need to retag it as a leaf. Okay, so this is just applying a function to a leaf and then retagging it as a leaf. Then we can look at the recursive case and figure out what we need to do. And again, let's think what we've got. So what we've got here is we've got a function G from A to B, and we've got two trees of A. So what could we do with that? Well, what we could do is we could recursively map the function across each of those trees. So I could write fmap G of L, and I could write fmap g of r. And by the type of fmap, fmap takes an a to b and a tree of a and gives me a tree of b's. So what have I got here? So here's an a to b, that's the function g. L is a tree of a, so when I fmap it, this whole thing here is going to have type tree of b. And it's the same on the right hand side. Here I have the function g, which goes from a to b. Here I have r, which is a tree of a. When I fmap it, again, that's going to give me a tree of b. So I've got two trees of b's now. I just want a single tree of b's. That's what the result should be. So of course what I do is I just write node here. Okay, so maybe you could have written this definition yourself straight off the bat, but I think for more complicated types, it's very, very useful to kind of write down the type of the fmap, then write down a skeleton and think, how can I use what I've got to build a result of the right type? And what we'll see in this course is that this process always works out in a very simple way. So this is the mapping operation for trees, and it does exactly what you'd expect. In the base case, it just applies the function to a leaf. In the recursive case, it calls itself recursively and then rebuilds a node again. So let's have a couple of examples of this, and then we'll think what actually is the point of functors. So the first example is if we fmap the length function, say, to a leaf which just has a string ABC. So this is a tree of strings. So the length function is taking a string as an input here, which is just a list, and then it's going to give us back the length of it. So you get exactly what you'd expect back here. You get leaf of 3. So this is simply applying the length function to the value in this leaf. A more interesting example is if we do fmap, if we take even, which is a predicate, it returns true if you have an even number and false otherwise. Let's apply it to a little tree of numbers or tree of integers. So if I get leaf 1 or leaf 2, then what it's going to do is exactly what we'd expect. It will find these leaves, apply even to 1 and 2, and we get back a tree of the same shape. So we're going to get leaf, so 1 is odd, so we get false, and 2 is even, so we're going to get leaf of true. So what we see is that if we apply fmap to any old tree, we get back a tree of the same shape, but we process the elements. So in this case, the element was, in the first case, the element was a list of characters, and we process it by taking its length. In the second case, the elements were numbers, and we process them by applying the even function to it to get false and true. So at this point, you might be thinking, well, okay, this is fair enough, but what's the point of functors? So why use functors? So there's a couple of answers which I would give to this. So the first answer is that we can use the same name, so the same function name, here fmap, for functions that are essentially the same. Essentially the same. So I could have defined manually, without using the functor machinery, I could have defined a mapping operation for the maybe data type, for the tree data type, for lots of other data types. But then I'd have maybe had to call them different things like map maybe, map tree, and so on. And that's a bit strange because they're basically the same idea. The idea of mapping is a kind of universal idea which applies to many container types like lists and maybe and trees. So why not use the same name for it? And then when I see fmap in my code, I know, oh, that's just mapping. I don't need to look at the definition. I know it's just the mapping operation for that particular data type. That's one reason we can use the same name for functions that are essentially the same. Another reason, which is an interesting one and a very powerful one, is that functors give us the opportunity to define generic functions that work for any functorial type. Okay, so we can define functions that work for any type which is an instance of the functor class. So what does this actually mean? So it's a really neat idea. So back at the start today, we defined the increment function and we defined the squaring function and so on, but actually these kind of functions are completely generic. So rather than defining the increment function to take a list of integers and give back a list of integers, because that's specific to lists, what I could do is generalize its type using functors. So I could say for any old functor f, the increment function takes an f of int to an f of int. So the type on the right hand side here is the main component of the type, and this generalizes the type of the original increment function. That took a list of integers to a list of integers, but now we're taking an f of an int to an f of an int. So f is any old parameterized type that is an instance of the functor class. So that means that it supports a mapping operation. So how can I define the increment function? Well, this is very simple now. I can just write fmap of +1. Okay, I just write fmap of +1, and now this is a completely generic definition which works for any type which is functorial. So I don't need to define an increment function for trees, and maybe I get it for free because I have made those data types into an instance of the functor class. So you can try this out for yourself in GHC. So you can type this definition in, start up GHCI, and then say what happens if I increment a list. Well, you get exactly what you expect. It just increments each of the components. What happens if I increment adjust? Well, it's just going to increment the 1 and retag it as adjust, so we'll get just of 2. And more interestingly, what happens if I increment a node? Well, suppose I had leaf of 1 and leaf of 2. What it's going to do is just map over that tree, and it's going to replace each of the numbers by its successor. So what we get back is we get node of leaf of 2 and leaf of 3. So that's basically it for today. We've introduced the idea of functors, which generalize the idea of mapping over lists to any kind of container-like data structure. And as we'll see in subsequent lectures, functors are the first stepping stone towards defining what a monad is. So that's it for today. See you again next time.